video, we are going to address measuring and constructing segments. Constructions only touching upon very slightly. Our primary focus is on this objective using length and the midpoint of a segment. Launching into it, these are the vocabulary words we will work with. Don't expect you to write them down, just know that these are the pieces that we will pop up with. So take a quick look at them and see, are there pieces you already know? Are there pieces that you don't know? Of course, if there are things you don't know, make sure that you emphasize learning that vocabulary, because the vocabulary is how we communicate with each other. If you don't know the words we're using, you can't talk with each other, or at least you can't talk math with each other. Okay, here's the first thing that we've discussed, or that we need to know. What is a ruler good for? Measuring distance. How many years have you been using rulers? I don't know, a lot. There is actually a piece called the ruler postulate, and basically it means it doesn't matter if you're choosing to use inches or feet or miles, the label doesn't matter. You can measure using a ruler. You can put a ruler down and say, here's 1 centimeter, 2 centimeters, 3 centimeters, 4, and just count them out, 1, 2, 3, 4. You can do the same thing with inches, 1 inch, 2 inch, 3 inch, 4 inches. 1 foot, 2 foot, 3 foot, 4 foot. 1 fish, 2 fish, red fish, blue fish. Point is, this is the ruler postulate. It just means it's possible to measure distance using a ruler. Again, postulates are things that you accept as being true without proof. Do you need me to prove to you that you can use rulers to measure distance? No, we're okay with that. But still, it has its name. Well, since rulers measure distance, of course, this tells us the big focus we want to know is, what is distance? Distance between any 2 points we will define with absolute value. Like we saw with our warm-up, we could take the absolute value of -8, and absolute value as distance has to be positive, so we switched it from -8 to +8. We will still use these vertical lines to represent distance between 2 points. And our advantage there is it doesn't matter if we wind up having a positive or a negative answer. When we're crunching our numbers, we know that distance has to be positive, and so we'll make it positive. For instance, here. Find the length BC. Well, let's pause before we start looking for an answer. Consider the notation. In our previous lesson, we saw things that look like this. Let's do a quick review as to what they are. What is the top one? Yes, that's a segment, because segments have endpoints, they don't have any double-sided arrow, or they don't continue going. What about the middle one? Array. It's a ray. Endpoint on the left, continuing through on the right. Third one. We've got a line. Well, each of those pieces we've mentioned have different behaviors because they look different. What if I don't draw anything on top at all? That's distance. It's a new piece of notation that we have to understand, because like before, if we start confusing these things, we won't be able to effectively communicate with each other. With nothing drawn on top, we're talking about the distance between 2 points. This is the distance from point B to the point C. On the second part here, that's the distance from point A to point C. We don't have a segment drawn because we're not talking about the object of a segment. We don't have a line. We're talking about distance. So, what is the distance from B to C? It's just asking us how far apart are 1 and 3. How far apart are 1 and 3 numbers? Well, we can do that simply by taking 3 subtract 1. done. We have our distance of 2. What happens if we got those numbers backwards then? What if instead we took 1 subtract 3? Following our add the opposite rule, 1 plus -3 is -2, which is why we were concerned with absolute value earlier. If we take the absolute value of 2, it's just 2. And if we take the absolute value of -2, it's still positive 2. Just remember, distance has to be positive. Now, you tell me, what is this distance between A and C? Thank you. We've got a distance of 5. Continuing further, let's find this length xy. What is the distance from x to y? 4. Close to 4. Not exactly 4, because check the location here. That's at 1.5. So this is a distance of half. 1.5, 2.5, 3.5. We can count out basically using a ruler and get this distance as 3.5. Another way we could have got that without counting, we could have taken y minus x, 5 subtract 1.5. And when we work through just addition and subtraction of mixed numbers, that would have been also 3.5. There are multiple avenues to get our correct answer. What about here on the right then? What is the distance from x to z? One, 2, 3, 4, and a half. We could have also obtained that by taking 1.5, subtract a -3. Following add the opposite, 1.5, add a +3, still gets us 4.5. We can count, we can use arithmetic, there are multiple avenues to get us where we need to go. This page is mostly just a definition and a notation piece. I want you to know this notation is massively, massively important for us. We will use it constantly throughout the entire class. You have to know what this symbol is. We say that segments are congruent if they are the same length. So basically, we could have stick in the left hand, stick in the right hand. These sticks are called congruent if they are the same length. If 1 foot matches 1 foot, then they are the same. And so we have these pieces that we can convert back and forth between each other. If we have 2 distances that are equal, and I want to emphasize this, distances can be equal, and then that forces the segments to be congruent. It's a matter of notation that we have to be careful of, because PQ distance is not the same thing as PQ segment. We can't use them interchangeably. They're not the same. One is length, one is the actual stick. It's the difference between saying I'm holding a ruler in my hand and I'm holding 1 foot in my hand. They're not the same thing. They're close, they're related to each other, but not quite the same. When we have segments that are the same, so they have this equal distance and are therefore congruent segments, we use tick marks. When we have 1 matching 1, that's telling us these things are the same. When we have more segments, we can match 2 tick marks with 2 tick marks, and that says they are the same. But if they have unmatching number, like 2 matching with 3, we don't know that they are the same. Or we could simply have here 1 tick mark on the right, 2 tick marks on the left. We don't know that they would be the same then. These tick marks are a way of communicating with each other, letting us know when things are the same or not. Next, we have this idea of betweenness. Colin and Dougie and Kaya. Notice how we've got all 3 of these guys in a row with their desks? We say Dougie is between Colin and Kaya. It's the exact same thing in math. Looking at this here, you notice how point A, point B, and point C are all in a line? They're collinear. You remember that term from the other day? Well, when we have collinear points, we can talk about betweenness. And if we have a point that's between 2 others, we can simply add them together. It's like saying the left part can be 3, the right part can be 8. So how long are they put together? I know you can do it. Please tell me. That's what we're talking about. This very simple idea is called the segment addition postulate. Remember, postulates are things that we accept as being true without needing approval. Well, you believe that if we put 3 inches next to 8 inches together, they're 11 inches? That's all that this is. It's just saying if we're using 2 pieces next to each other, their individual lengths add up to the total length. This part right here is the primary focus behind our lesson today. Most of our homework is going to use this. So the biggest amount of practice you're going to be using are based on creating pieces and finding the lengths of segments, whether they're very quick with numbers or we have to build algebraic equations and solve them. So let's run through this. G is between F and H. FG is 6, FH is 11, find GH. Okay, so what's that saying? Can you create a picture for it? You have an idea of what it looks like? What does this piece mean? G is between F and H. Okay, so I have F, I have H, and G is between them. I'll put G here. FG is 6. FH is 11. So the whole thing is 11. How big is GH? 5. We've got our answer. How'd you get it? Subtract 6 from 11. We're done. Don't be tempted. Sometimes students are tempted where they think segment addition postulate and they just say, oh, I'm going to just add these numbers together, and they say 17. Make sure you're paying attention to which lengths they're given. Because as we saw with this one, it might be that you're given the whole and a part. And you have to figure out the second part. Okay, a little bit trickier now. M is between N and O, so we've got our diagram. Find NO. So what have we got then? How can we build an equation based on this? Because that's what we need to do. When we're given variables and these variable expressions, we're going to have to build equations and solve them. What's our relationship then? What does the segment addition postulate tell us to do? Part 1 plus part number 2 will equal the total. That was supposed to be in yellow. That's the relationship that you have to know. Massively important thing that we'll work with. If you add the pieces, you get the whole. So we have part number 1 plus part number 2 will equal the whole thing. At this point, the geometry is basically done. The geometry part of this is recognizing what you're supposed to do. It's knowing what the segment addition postulate is. We've basically changed this then from a geometry problem into an algebra problem. So let's go through and do our algebra because we've already passed that class. We know what we got to do. What's our first step? Put our like terms together, and so do you want to move the 3 over or do you want to move the 5 over? It's your choice. Moving the 3, so we'll subtract 3x, which then gives us 17 minus 5 equals 2x plus 2. Now what? What's the next thing? And there's more than one correct answer to that. For me, I'm going to combine that 17 minus 5. 17 minus 5 gives me 12. Then what? In 2, we're going to subtract 2. Scroll this thing down, so 12 subtract 2 is 10. Finish the problem out here. Divide out by the 2, and we get 5 is equal to x. So we've got this answer that x is equal to 5. Is that what we were asked to do? Not by itself. We definitely needed to do this, but the directions did not say find the value of x. What did the directions ask us to do? Find the value for NO. What is the distance from N to O? It's right here. That distance is 5x plus 2. But after all the other work we did by setting up the equation and solving it, we know x is equal to 5, so we can just plug that right back in. 5 times 5 plus 2. And now we're back to some pieces with pre-algebra with evaluating the order of operations. Five times 5 gives us 25. 25 plus 2 is 27. And we finally have our answer of 27. Continuing further, the midpoint is a special type of betweenness. In particular, a midpoint cuts a segment in half. And when you cut something in half, we call it bisecting. So, in terms of a drawing, we can have the segment AB, which has a total length of 6. Well, what length is going to cut this thing a length of 6 perfectly in half? What's half of 6? 3. And so if we put a point M, and I'm using M for midpoint, I'm taking a letter that reminds me what it is, M for midpoint, that midpoint has to chop it in half at 3 and 3. Another piece of vocabulary that is going to be very, very important for us, because with geometry, looking at things that are perfectly in the middle is a pretty important concept, especially early on. So you do need to know this vocabulary of midpoint. You are supposed to know bisecting. These are terms that we will use frequently. And you're expected to know what midpoint and bisect are. That way when I say them, you'll understand what we're talking about. And I also expect you to use them coming back so that we can understand as well. So consider this, our last example for today. Here's a map showing a route for a race. You are standing here at X, 6,000 feet from the first checkpoint of C. Okay, so we'll put that down. The first segment is 6,000. The second checkpoint is located at the midpoint between C and the rest of the race. Make sure we understand what that's saying. The second checkpoint of point D is at the midpoint from C to the end. That sentence right here, when you read that, you should recognize then that since D is the midpoint, those two chunks have to be the same. That's what the sentence is telling us. The total race is 3 miles. And since there are 5,280 feet per mile, there are 15,840 feet in the total race. So the whole thing is 15,840. We're wondering, how far apart is that? Well, I'm hoping that you see in the red, we've got the segment addition postulate going on. We can simply subtract off that 6,000 and get 9,840. This 9,840 is how much is left for the combined pieces. We can cut that combined piece in half because it's a midpoint. And just dividing by 2 then gives us 4,920. And that's what we're looking for. How far are these two chunks? Each of them are 4,920 feet. We had to combine the segment addition postulate along with our understanding of midpoint to get those